today, that's what I'm going to be talking about, specifically from the perspective of the quality of security, is what can you as an architect do to create a more secure system? Oh, and I should say that this is joint research with Professor Jungwoo Ryo at Penn State and Professor Humberto Cervantes at blah, blah, blah in Mexico City. I'm not going to try and mangle that. Okay, so software security is a complex problem, and it's a multidimensional problem. So if you think about what you need to do to make a secure system, yes, you need to code securely, or you need to avoid making the kinds of security bugs in coding that a hacker can exploit. But security also involves policies like patch management. It involves operation. It involves human processes like make sure you know who it is you're talking to when you're giving away confidential information, and don't give your password over the phone, and these kinds of things. However, most of the software engineering effort into security, up until very recently, has gone into coding. Just coding, even though it's a multidimensional problem. I shouldn't say just, but the majority. Part of the Software Engineering Institute is CERT, the Computer Emergency Response Team. That's about half of the SEI. So it's a big group of people, maybe 250 people, all furiously working away at trying to improve the security state of our software. And even amongst that group, most people focus on coding. So why is this? Why don't we think about design? So my contention is that secure coding, while obviously necessary, is not sufficient to ensure a secure system. Secure coding isn't enough. And again, why isn't it enough? If I code securely, if I make sure that I know the length of my buffers, and I'm escaping characters that I get from input from users, and all those kinds of things that we do to avoid buffer overflows and cross-site scripting attacks and these kinds of things, shouldn't my code be secure? Well, here's the problem. Security is a weakest link phenomenon. If I, as a programmer, I'm in a rush, I've got a deadline pressure, and I make some ugly hacks in the software that I have to deliver, and those ugly hacks perhaps compromise performance or compromise the modifiability of the system. We've all done this. The system becomes a little less modifiable, right? We've coupled two classes that shouldn't be coupled. We didn't put in an abstraction that we should have put in, something like that. The system's a little less modifiable. Or if I change an algorithm and make it a little less well-tuned, perhaps the system is a little bit slower. I've increased latency slightly. But with security, I don't make the system a little bit less secure when I introduce a security bug. It's an all-or-nothing phenomenon. If a hacker can find and exploit that bug, they're in. The system is completely insecure at that point. So we cannot treat security the same way we treat other quality attributes of software. Another reason why secure coding isn't enough is that secure coding practices are expensive. They involve a lot of code reviews, a lot of manual scrutiny, a lot of penetration testing. And these things are time-consuming and expensive. So this doesn't bode well for the software engineering community. It seems like we've got a really steep slope to climb, and if we make any mistake, we're dead. So for this reason, I'm advocating an architectural approach to security. Again, I'm not saying secure coding is unimportant. Clearly it's important. But I'm saying that you cannot ignore architectural issues. You should not ignore architectural issues if your goal is to make a secure system. And specifically what I'm going to be talking about today is the use of security frameworks as a means of achieving higher levels of security. Security frameworks encapsulate best practices in both design and coding. And so for a number of reasons, I will argue that this produces better outcomes for security, and outcomes which are going to be extremely difficult to achieve except through architectural means. Okay, so that's my claim. What's the evidence for this advocacy? Sounds reasonable, but lots of things sound reasonable that are wrong. So what's the evidence? Well, until now, no evidence, just opinions, like an awful lot of software engineering. So what I want to present to you is the results of 3 case studies that we did about 9 months ago, and we have another case study which is ongoing using this methodology. And what we did is we looked at the consequences, the effects of using a security framework on both system quality, specifically the security of the system, and I'll tell you how I measure that in a minute, and also development efficiency. Right? In software engineering, especially in the quality assurance portion of software engineering, but I guess it's true in software engineering in general, we're always fighting cost and schedule constraints. So it's not simply a matter of what can I do to make my system more secure, but what is the most cost-effective means of making my system more secure. So to explain how I think about this, I want to first talk about the architectural foundations for security. And there are 3 things that you can do as an architect, 3 design approaches that you can take towards security. So these 3 related concepts are tactics, patterns, and frameworks. Now, these concepts actually apply to any quality attribute. So there are tactics, patterns, and frameworks for performance, for modifiability, for availability, for testability, for usability. But here I'm going to focus on the set of design primitives that specifically apply to security. So tactics are probably, of those 3 concepts, the concept that you have heard of the least. But what a tactic is a primitive technique that an architect can use to achieve some quality attribute or quality attributes in a system. And the tactics that I'll be talking about today are all taken from my book that Ewan mentioned in the introduction, Software Architecture and Practice. So what's a tactic? A design primitive. It's a design choice made by an architect to achieve some quality goal. So before I talk about security, let me give another example. Let me talk about availability. As an architect, if you want to create a highly available system, there's only a handful of things that you have at your disposal to do. So first of all, you have to have some way of detecting that a fault has occurred. So what can you do to detect a fault? Well, you can use exceptions. You can use ping echo, where you have some component that pings another component, and if that component doesn't echo back, you say that component or the connection to that component is down, is dead. You can use a heartbeat in a monitor, where the component you're monitoring is supposed to be periodically sending out heartbeats, and you're monitoring that, and if you stop hearing heartbeats for a certain period of time, you say that it's dead. And so forth. So there's a small number of things that we can do as architects to detect that a fault has occurred in the first place. Once we've detected that a fault has occurred, we now have to choose how to respond to and recover from that fault. So for example, we could have a cold spare. You keep a spare server in the closet, you wheel it out, you plug it in, you load data, you start it going, you connect it to the network. Okay, that's one way of recovering from a fault. It's probably not going to give you a high level of availability, but maybe it's adequate for your needs. You could use a warm spare. That's where you have an active server paralleling, a standby server paralleling the active server, and the active server sends periodic updates, and so if the active fails, the other one is in a warm state. It only needs to collect or recover the data since the last update to get into a fully active service. You could use a hot spare, where every transaction that goes to the active server also goes to the backup server, and it's ready to take over at a moment's notice, and so forth. So tactics describe each of these design primitives, each of these design options for the architect. Tactics are more primitive than patterns. A pattern is a collection of tactics, because a pattern typically is a collection of several design decisions which collaborate to achieve some goal. So if you think about an availability pattern like triple modular redundancy or quad modular redundancy, the sorts of things that flight control software in modern jets use, well, it's a combination of some sort of heartbeat and monitor and hot spares and a voter. So it's using several tactics put together into a pattern. So this is no different for other quality attributes like security. So we've identified a set of security tactics. Every set of tactics is hierarchically decomposed. So you start off with the design goal. So for security, you have to have a way of detecting attacks. You need a way, or you may want to have a way of resisting attacks. You may want to have a way of reacting to attacks, and finally recovering from attacks. If you want a secure system, you have to know that you've been attacked. You probably want to resist attacks. Given that you won't be successful all the time, you need to react to the attacks, notify the appropriate authorities, turn off sources that are the attack vectors, lock down resources, and finally you want to recover from attacks. Restore data, inform people, audit the activities so you can go after the bad guys and so forth. So tactics provide a vocabulary for both design and analysis. Patterns do too, but patterns are more complex. A pattern is a bundle of design decisions. Each tactic is more primitive, is more simple. However, because they're primitive, realizing tactics in code requires a lot of interpretation. So tactics for resisting attacks, for example, are things like identifying, authenticating, and authorizing actors. Well, those are easy to say. How do I actually do that? Well, one of the ways that we do that is via patterns. So we implement or realize tactics, which are primitive, with patterns, which are still abstract, but a little less abstract, a little closer to code. So there are a number of well-established security pattern catalogs. There are books of security patterns. There are websites of security patterns. And patterns, excuse me, patterns help to structure a design. They give you a starting place for design. They give you bigger chunks of design than individual classes to deal with and to reason about. But again, they're difficult to correctly implement, they're difficult to maintain, they're difficult to combine with each other. So if you've ever tried to implement a pattern out of a patterns book or a patterns website, you would never implement the naive version of the pattern. You would never just go ahead and implement the structure that's there because it's underspecified. Right? If you go to a website and look up the broker pattern, and what you will see is a broker. Well, what if that broker goes down? What if that broker gets overloaded? How do I test that broker? How do I ensure that only the right people are using that broker? How do I authorize that broker? So When you actually get into the real world and want to implement patterns, there are lots of other decisions, lots of other information that you're going to have to add to turn that pattern into code. The third fundamental design concept are security frameworks. And a framework, I'm sure you're all familiar with frameworks, you're experienced developers. A framework is a reusable software element that provides generic functionality that addresses some set of recurring concerns that you see over and over again across a broad range of applications. And there are many security frameworks out there. There's just a few examples of frameworks that are either specifically for security or that include a significant security portion. And these exist for many different technology stacks, many different languages. Frameworks are good because you get a lot of functionality when you adopt a framework, but they often have a very steep learning curve, and there's a lock-in effect. Once you've chosen a framework and coded to that framework, you're going to pay a fairly steep price for switching to a different framework, both in terms of redesign and coding effort and also the assurance, the testing, the requalification of any system if you choose to change framework. Frameworks instantiate or realize patterns. So frameworks embody patterns. They're built around patterns. So these three fundamental design concepts are all related to each other in a kind of hierarchy of abstraction. Okay, so those are our basic architectural design primitives: tactics, patterns, and frameworks. Those are the things that you can use as a designer, as an architect, if you want to build a secure system. That's your palette. So now, given this wealth of design concepts, we were interested in understanding how architects actually approach security and how well these different design concepts, these different design primitives, actually perform in terms of securing the system, actually achieving a high level of security, and reducing costs, reducing the cost of creating the architecture and maintaining the architecture, right? So you're interested in both cost and quality, obviously. So here's what we did. We looked at three different systems, and you can see the names of the systems there on the left. Code One is a company in Korea. They are themselves the creator of a security framework. They're also a security consulting service. And they were hired by a third party to improve the security of that third party's web application. So that third party had created, I'm not allowed to say who they are, but they had created a web application. They were continually being attacked and brought down. They hired Code One to go in and refactor the system to improve its security. So the framework that they employed was Code One's homegrown framework. Second case study was QuarkSoft. That's a software consulting company, a medium-sized enterprise in Mexico City. And the system that we looked at was an internal project management application, web-based application. So they're a consulting company. They've got lots and lots of projects going at the same time, and management wanted a single portal essentially for tracking the various projects and tracking cost and status and so forth. So this was their internal web application, and they used the ZK and Spring security frameworks primarily for addressing security. And the third example was OpenEMR. OpenEMR is a electronic medical records system, an open source project, and they employed no frameworks whatsoever. So they hand-coded all of their security. Okay, so what did we do? First thing that we did was we interviewed the architect on their approach to security. We asked the architect, what have you done to ensure that your system is secure? What is your design mindset? What are your design approaches? What design primitives have you employed to get a secure system? We also asked about the size of the system and what percentage of total project effort went into security. So that was an estimate. The other thing that we did was we scanned each of these systems using AppScan, which is pretty much an industry standard security scanner. It's from IBM. And our goal here was to understand the trade-offs. The trade-off space between the costs and benefits of different approaches to security, to understand if one or more of these design concepts represents the right way of approaching security, or an optimal way of approaching security from an architectural perspective. Okay, so probably the least obvious part of this protocol is the actual interview. So there were 6 parts to this interview. First is we asked the architect, what were your primary drivers? What were the most important quality attributes in the system? And among those, where did security fit? Second thing we asked is, well, how did you actually achieve whatever level of security you've achieved in the system? What did you do as an architect? What did you design into the system? And how do you reason about the trade-offs? Nothing is for free. So if you're making the system more secure, did you reason about the consequences on usability or on performance or on modifiability? Fourth is architects architect. They create designs. How do you ensure that what your developers develop conforms to what you've designed? How do you know that that mapping is a faithful one? Because if you've developed a beautiful, lovingly constructed system, and with, let's say you've used a single access point pattern. So to get at certain key resources in the system, everyone has to go through a single access point. And then developers go and develop whatever they like, code whatever backdoors they like. What have you got? You have an insecure system, right? Security is an all or nothing quality. So we wanted to know, how do they ensure conformance? How do they know that the developers really followed whatever design principles they had baked into the architecture? As I said, we asked about their estimate of project effort, how much effort goes into security as a percentage of total project effort, and if we asked them both with and without a security framework. So if they could estimate both ways. And then there was an opportunity for other questions. Now, of these questions, number 2 was guided by our tactics hierarchy. So when we asked about the approaches to security, what we essentially did is take each tactic, each security design primitive, and turn that into a question. So for example, detect intrusion. We said, does the system support the detection of intrusion? So typically, if you're going to detect an intrusion, you're going to compare network traffic or some kind of service requests, the patterns of service requests with known patterns of good or bad behavior. And if you detect a pattern of malicious behavior, you say, we're under attack now. We need to do something. How do you detect a service denial? Similarly, you're going to look at signatures of network traffic to see if you're experiencing an attack based on its similarity to patterns of known attacks. Does the system support verifying message integrity? So do you use checksums or hash values to ensure that a message in transmission hasn't been tampered with? Do you detect message delays? So if you can monitor how long it takes, or you know historically how long it takes for messages to travel from point A to point B, detecting an anomaly in that time might be a way of determining that you're experiencing a man-in-the-middle attack. Does the system support limit exposure? So sometimes this is called don't put all your eggs in one basket. So is there a way of partitioning the system's resources or services, such that if one part of the system is attacked, you don't compromise all of the system? So this is just, 5 questions. We had about 20-ish questions, however many tactics there are, one for each of these. The entire interview took about an hour. So this is not an onerous task for the architect. An hour, hour and a half. And then example answers. How do you detect intrusion? Well, we use hardware firewalls, and Spring Security guarantees that a session comes from a single place. How do you detect a service denial? Well, that's covered by the ZK framework. Let's see. How do you identify actors? Well, that's covered by Spring Security. How do you authenticate actors? Blah, blah, blah. So for each of these questions, the architect would essentially say what they did, or in some cases, what they didn't do. How do you limit exposure? Well, that's not covered. How do you encrypt data? We use HTTPS. Do you have a way of automatically changing default settings? No, we don't do that. Do you have a way of automatically informing actors that you're under attack? Right? Let's say you've detected a denial of service attack. You've detected an intrusion attempt. Does anybody get notified? Does anybody's cell phone start ringing? Do you have a way of restoring resources in the event that you have been attacked and resources have been compromised? No, we're not doing that. We also collected some metrics. So the vulnerability metrics were collected using AppScan. So AppScan categorizes vulnerabilities as high, medium, or low, or informational. We were primarily interested in the highs. Those are the things that can really bring down your system, expose you to major losses of information or losses of privacy. We measured the size of each of these applications in lines of code, and as I said, the interviewees, the architects, estimated the effort involved. Okay, so in our case studies, we essentially had 3 different approaches to security. That was just fortunate. We didn't plan that way. We just had these various opportunities to do case studies, and it turns out that they covered the spectrum of approaches to security in terms of their degree of adoption of frameworks, in terms of their architectural or system-wide systematic approach to security. So full adoption. QuarkSoft used security frameworks from the beginning. They designed based on security frameworks throughout the lifetime of the project. The Acme project, the one that was maintained by Code One in Korea, they introduced the security framework in the middle of the lifetime. So we distinguish in our analysis Acme before and Acme after. And finally, no adoption. That's the case of OpenEMR and Acme before. They don't use any framework whatsoever. They do not have a systematic, system-wide architectural approach to security. And here are our results. So first of all, you can see the approach, Acme before, no adoption. OpenEMR, no adoption. Acme after is partial adoption using the Code One framework. And QuarkSoft used the 2 frameworks mentioned. These are the vulnerability measures on the 4 systems. So 0 is good. Anything that's not 0 is bad. Right? The absolute values of the numbers are less important. What's really important is it's not 0. So the only systems that achieved zeros were Acme after and QuarkSoft. Based on our interviews, we counted the number of tactics, the number of security tactics that each of these systems supported. And you can see that QuarkSoft and Acme after both supported a relatively high number of security tactics, about 2/3 of the entire set. OpenEMR and Acme before, much lower. But what's even more interesting in these numbers is the number of tactics that were implemented in business logic. What this means is how many of these did you code yourself versus how many did the framework handle for you. So QuarkSoft, they didn't code any of those security tactics themselves. The ones that they used were all and only the ones provided by the frameworks. Acme after did 5 of the 12 in business logic. Acme before, 5 of the 6 in business logic. So I guess that's the same 5. and OpenEMR, 6 of their 9 was in the business logic. Oh, and finally, estimated effort. So what we see is that the 2 no adoption cases, they estimated 20% of their total project effort went into security. Coding, quality assurance, audits, walkthroughs. QuarkSoft estimated 3%, and we asked the architect, how much do you believe it would have been had you not used the frameworks? And he estimated it would be 30%, which is pretty close, in the ballpark of the 2 other instances and no adoption cases. And finally, Acme After, they estimated that about 10% of overall project effort went into security. They were the partial adoption case. So these results paint quite a nice picture, quite a consistent picture that you take an architectural approach, you get better results at substantially lower costs, order of magnitude lower costs. So, inferences from the results. This is case study research, so we're not claiming statistical significance here, but the results were extremely consistent across these case studies. And as I said, we're currently pursuing a 4th case study. And it seems as if using an architectural approach to security as realized in a framework is superior both in terms of effort and in terms of the actual result, the number of vulnerabilities. And even partial adoption gives you some of those benefits. But the effort for partial adoption is significantly higher than the effort for full adoption. So again, we get a consistent spectrum of results. So, not surprisingly, we recommend the use of security frameworks from the very beginning in the construction of the system. We recommend the full adoption. And this seems like a fairly obvious result, except that, as I said, there was no evidence for this advocacy prior to this. Clearly, I say, it seems reasonable that adopting a framework after the system has been built will be much more costly than doing it from the start. So partial adoption is a suboptimal, but frankly a very common way of using frameworks. We often see systems that began as skunkworks projects, they grew up, and at some point they said, we need to get our act together on security, and then they went and started trying to reverse engineer and refactor the system to use frameworks. And this is because most developers and architects worry about functionality first and security and other quality attributes later. Right? Get those user stories done. And then we'll worry about that software engineering stuff. And this is one of these attitudes that makes you think you are being productive early on, when in fact you're really shooting yourself in the foot long term. Okay, so why is it best to address security via frameworks? Well, a number of consequences. First of all, application developers should be, and hopefully are, experts in their domains, but they are typically not security experts. It takes a long time and a lot of specialized training to become expert in security. It is its own domain. And even if developers are experienced in security, they should not write their own security controls, for the same reason that you shouldn't be the only one that tests your own software. You're going to be blind to the assumptions that you made in your design and in your coding. So even if you're experienced, you should not be the one writing your own security controls. Finally, using a security framework increases the likelihood of conformance, increases the likelihood that the security controls will be applied consistently. So when we talk to the OpenEMR architect, for example, what they did was they were constantly very busy finding security bugs and fixing them, and finding security bugs and fixing them. And they were treating each security bug as a unique phenomenon. And therefore, in fact, treating each interaction with the user as a unique phenomenon, and therefore they didn't have a consistent approach to security. They didn't have a system-wide approach to security. Every interaction with the user had to be secured separately. And finally, this is just an efficiency argument that if you delegate security, or any other quality attribute for that matter, to a framework, this allows your developers to focus their energy and their creativity on application logic, the things that customers pay for. Because customers don't pay for security, they punish you for lack of security, right? It's seldom that you can sell a system because it's more secure, but you will certainly lose customers if it's less secure. So it's one of those cases where you have to have it, irrespective of what the customers believe their requirements to be. So finally, we are, as I said, we're currently pursuing additional case studies. We have a case study that we've just begun recently with a company that develops stock trading software, and so we anticipate that this company is highly motivated in the security area. So hopefully in a couple more months I can report on the results of that study. So with that, I'm happy to take questions. Thank you. Yeah. Well, that's a reasonable question, and that should be asked of any commercial product, COTS product, open source product, not just a framework. So we've been working with a number of industrial partners who basically have evaluation labs. And so they evaluate not just security frameworks, but all kinds of products. And we've come up with essentially an evaluation process that we use and a scorecard that we use, because you're not only interested in the effects on security, but the effects on performance, the effects on maintainability, testability, and so forth. So we have to evaluate on multiple dimensions. So as I said, security is a weakest link phenomenon. So having secure coding, I said, wasn't enough. Having a good design obviously is not enough. If someone has physical access to your network or to your servers or something, then all the software security in the world is undermined. The standard technique for addressing those kinds of issues, and I didn't talk about it here, is threat modeling, and trying to essentially you build a system diagram, a context diagram, you look at the data flows, and then you model the threats going into and out of the system. So that's the sort of thing that we do at the Software Engineering Institute. However, that is pretty much an art. So I've participated in some of these exercises, and I've read about some of these exercises, and no one can tell me how to craft an attack surface and how to know whether I've gotten the attack surface complete and completely correct. So you need to do it. You need to get it right, but I'm not aware, for that particular example, of a systematic and thorough way of doing that. So for the foreseeable future, there's still aspects of security that are an art. Yes? I will do my best. So my understanding of what you're asking is there are architectural mechanisms, and you gave persistence as an example of an architectural mechanism, and you're asking how tactics, patterns, and frameworks intersect with those and affect the... Yeah. So a mechanism is typically has to be realized by something. You have to code it yourself, or you have to use a pattern or framework. So you gave the example of persistence. Let's say I want to do, I need to persist some data, and I have a database for persisting that data, and then I need access to that data, in my system, so I might want to do object relational mapping to that database. Well, there are frameworks like Hibernate, which can allow me to do that. There are tactics like caching, which allow me to address the performance consequences of that choice of architectural mechanism. So an architectural mechanism will have to be realized by tactics, patterns, or frameworks. And the nice thing about them, these, if you read a patterns book, you will see that there are the pros and cons of every pattern are listed. The consequences of using each pattern are listed. And so that gives you some insight as to the trade-offs that you're going to make in employing that. So if to continue with that example, if I use caching, then I'm doing that to improve performance, but I'm going to increase system complexity. I'm going to make the system a little bit harder to maintain and modify, because now when the schema changes, perhaps I also have to change the cache. I have multiple access mechanisms and so forth. So nothing comes for free in design, but these give you a guide or insight into the quality attribute consequences and trade-offs of these design choices. Yes? A number of years ago, oh, sorry, repeat the question. So the question was, since I talked about trade-offs, how does QFD, or quality function deployment, sometimes called the house of quality, how does that relate to what I'm talking about? So, not too much. I've seen it used at kind of system level analysis for the, let's say, the broad brush analysis of a system. You know, if we do this, it'll make the system a little bit more of this and a little bit less of that. So I gave a lecture at University of Auckland this afternoon, and one of the things I talked about was in civil engineering, every building architect, real building architect, knows the pluses and minuses that come from steel construction versus reinforced concrete construction. Those are well understood trade-offs, and those are the kinds of insights that QFD gives you. But if I want to understand the specific trade-offs in a specific design choice, so let's say I use ping echo to help in availability. How quickly should I ping? How frequently should I ping? I can know from general knowledge of the use of that pattern that the more frequently I ping, the quicker I can detect a failure, and the more frequently that I ping, the more I'm wasting computation and network resources on messages that almost all the time are useless. So there's a trade-off between performance and availability. But as to the specific value that would be right for any given project, QFD won't tell you. Only analysis or prototyping will give you that level of architectural insight, analysis insight. Yes?
So talk about the effort required. Did you also take into account the cost of these frameworks?
Okay, so the question was, did we take into account the cost of these frameworks? And no, we didn't. In fact, most of the frameworks that we've looked at are open source, but certainly there are lots of commercial frameworks. So yeah, that's a fair question, and we didn't look at that, but I think I'll have to add that question to our survey. Thanks. Yes, the back. Yeah, so the question was, what about the cost of adoption? So I mentioned earlier in the talk that frameworks have a steep learning curve and there's a lock-in. In the case of QuarkSoft, the architect and his team already had extensive experience with those frameworks. So yes, that would be another dimension of cost. If you're adopting a new framework, that will be a upfront cost that you'll have to absorb, or you'll have to consider in the cost-benefit equation.
From your experience, how many companies are proactively
Yeah, so the question was how many companies are proactive in dealing with security and how many are reactive? Is that it? Yeah. Well, I have not done a thorough analysis, so I'm just going to give you my impressions. I've been doing architecture analyses for over 20 years and in industry. Most of my analyses are in industry. And what I find is that most commercial software is reactive on every quality attribute. That there's an awful lot of we hack, and then when things start getting really bad, then we take a step back and we think about maybe think about refactoring, or maybe we just tighten our belts a little bit and hunker down. The state of the practice is getting a little better, but I would still say that the majority of systems that I have come into contact with have not been consciously designed or consciously analyzed, at least not thoroughly. That a lot of properties are emergent. That a lot of companies, I'll go in and I'll ask, they've got a big, complex, mission-critical system. Who's your lead architect? Right? There is no one even with that role in many cases. So, as I say, I do see the situation as improving over the years, but I still think that systems that are consciously architected are in the minority. Yes?
How's that IBM test work?
So, okay, so the AppScan, essentially what AppScan does is you have to make your system available for scanning, which means you have to identify the ports on which the system is open, because otherwise it can't scan if it can't get access to the system. And then it does essentially a penetration test. So it's going to run through large numbers of different kinds of tests to look for buffer overflows, to look for, if I can enter text in a field, can I enter a really, really long text? Can I enter some JavaScript and get that to execute? Can I enter a SQL command or a portion of a SQL command, and so forth? So it's a kind of pattern-based, you'd call it a testing tool that attacks your website, and for the same reason that you have a separate QA group, you don't want to be doing that yourself. Sorry, say again?
The people that make the frameworks probably use tools like that to make the frameworks better.
So the comment was the people who make the frameworks perhaps use that to make their frameworks better. It's possible, but those tools only work on systems, not on frameworks. So I could imagine building simple systems with a framework and then using something like AppScan to test it. But I think in a lot of cases the framework users rely on their community of customers and their own experience and their own internal test suites. They are the security. So the question was, are there economies of scale? Do larger projects expend relatively less on security? I haven't looked at that question. My hunch is that the economies of scale are not related so much to size, let's say, in terms of lines of code, but rather in, again, in this architectural approach, that if you are doing things manually and you've got a small system, it's probably cheaper to do it manually because you don't have to pay the adoption cost of the framework. You don't have to go through that learning curve of a framework. You may not get excellent security results, but just purely in terms of cost, it's probably cheaper. But again, my hunch is that that trade-off point is relatively low, that you don't have to have a very big system before it's going to pay for you to do it, to use frameworks. Okay, thank you.
Okay, well, Pete's will be here in a few minutes, hopefully, fingers crossed.